Okay. Okay. So our next speaker needs no introduction. Toby Colding is one of the leading figures in the theory of minimal surface and harmonic functions. He received his PhD in 1992 from UPenn. He was on the faculty at Courant from 1992 to 2008. And since 2005, he has been a professor of mathematics at MIT. He's a member of Royal Danish Academy of Science and American Academy of Arts and Sciences. He has several awards and recognitions, including AMS Oswald Veblen Prize in Geometry in 2010 and Simon Fellowship. He was an invited speaker in ICM 1998, and he was a plenary speaker in ICM 2022. So we are very, and he's going to talk about geometry of PDEs today, and we are very pleased to have Toby Colding with us. Okay, thank you very much.
Great, thanks so much. Yeah, so I'll talk about geometry of PDEs or geometry and PDEs. And so let me just make sure I can get it to work here. So, right, so often, so let's see, right, so often the geometry is, so we talk about geometry analysis, and often the geometry unlocks the structure and leading to fundamental tools in PDE. And so we'll try to understand equations that require insight in both analysis and geometry, plus the interplay between the two. And I will discuss this in various examples. In particular, so optimal geometry and evolutions of shapes are governed by PDE. The geometric invariance means that the PDE is canonical, and it means also that the naturality also means that the same type of equation appear over and over again across many diverse areas, and the equations describe phenomena that seemingly are unrelated to geometry. Right, so I just got confused on the first slide, so let me just say this so you don't get confused. Somehow it's the slides have been, I'm not sure why, but it has been reflected. So it actually is the slide, the order of the slides is on this particular screen. The order of the slides is the one to your right. So the geometry of PDE, that's the first slide. It's somehow, I'm not sure why it have been mirrored here, but that is the natural first slide. Okay, so what I want to do is I want to emphasize.
Can you share only one slide?
Yeah, no, I don't. Unfortunately, I can't because I tried that earlier.
I see. Okay, yeah.
And I can do that, but if I do that, then I can show you. I can do that, but then some of it is unfortunately cut away. So it will be like this. Is that okay?
This is better. Yeah, this is better.
Okay, great. Okay, so what I want to do is I want to emphasize a few big ideas and themes, and I want to suppress various aspects and results. But my hope is that it will, by emphasizing these few big ideas and themes, it will give you an idea of a large and very active area. And I'm going to focus on joint work with Bill Minicotti. And so the interplay between analysis and geometry we'll see that in particular in three examples. In how to show optimal regularity in PDE, in stability of solutions, and in the geometry of the diffeomorphism group. So these are the three areas that I will emphasize. And so the first example here of this is optimal regularity using geometry. And so in PDE, one often have existence versus regularity. So in PDE, existence is often shown in a weak sense, and that could be either in a distribution sense or in a viscosity sense. And that's typically done, that's typically relatively easy by very general methods. The challenge is then to prove regularity. If one is dealing with a nonlinear PDE, then weak solution might not be smooth. And one asks, how smooth are the solutions? How big is the set where the solution is not smooth, so the singular set? The second example of this interplay between analysis and geometry will be stability of solutions. So in dynamics and PDE, a central question is which solutions are stable, which are not. The stable ones are the ones that physically happen, whereas the unstable ones are not seen in nature. And so we come back to this example. What you see here is on the slides, and this moving from left to right, is that you're looking at a soap film. The soap film is what's called a catenoid in this case, and it's a large piece of the catenoid, and that is unstable. So it is in equilibrium, but it's highly unstable. So any movement will immediately force it to completely change. So it's an unstable solution to a variational problem. And so you wouldn't really see this in nature. The third example of this interplay between analysis and geometry is in the geometry of the infinite dimensional diffeomorphism group. And so their geometric property, they are universal. They are independent on which coordinates you look at them in. But if you're looking in different coordinates, objects may look very different in different coordinates. And so the question is then, how do we recognize geometric objects when there's no natural coordinates? And to do that, the key is to understand the group, the geometry of the diffeomorphism group. So these are the three examples that I want to discuss, where we have this interplay between analysis and geometry. The first is in proving the challenge of proving regularity for solutions that are given by a very weak, often functional analysis point of view. Given the existence is given by a very weak technique. The second example is that of stability of solutions. And the third example is in the geometry of the infinite dimensional diffeomorphism group. So now let me come to some of the equations, or at least the first of the equations that I want to look at. And that equation comes from surface tension. So surface tension gives a PDE that describes evolution of shape. Mean curvature is the force of surface tension. Surface tension causes water to form roughly spherical droplets. And so mathematically, again, surface tension is the mean curvature. The mean curvature is the sum or the average of the principal curvature. So if you have a surface, the average or sum of the principal curvature is the mean curvature. And so if that surface is the level set of a function, we say it's a level set of a function u, then the unit normal is a normalized gradient, so the gradient divided by its norm. And the mean curvature is then just the divergence of the unit normal. If you have a surface and the surface tension is the only surface, the only force acting, then the surface is in equilibrium when the mean curvature is 0. And that means that is what's called a minimal surface. A minimal surface has a long history beginning with work of Euler and Lagrange in the work of Euler is from 1740, and the work of Lagrange is birth of calculus, a variation that goes back to 1755. So it has a long history. Mean curves of flow. So that is when things are not in equilibrium, but moving towards equilibrium. So a surface is said to evolve by the mean curvature flow if each point is moving normal to the surface with speed the mean curvature. So in other words, the time derivative of the position vector is minus the mean curvature times the normal to the surface. And so this movement has a smoothing, automatically a smoothing effect. So if you're looking at so this here is, the surface is the boundary of this light blue region. And if you're looking at say this point here on the surface, so surface again is the boundary. If you're looking at this point here on the surface, this is a convex point. Under the mean curvature, it will move, mean curvature flow, it will move inwards. This is another convex point, it's also moving inwards. Whereas here you have a concave point. So a concave point will move outwards. And so, right, so it has this automatically smoothing where convex points move inwards, concave point move outward. So mean curvature flow is it's a nonlinear heat type equation. It's a negative gradient flow for area on the infinite dimensional space of surfaces. And the flow makes the area shrink as fast as possible. Mean curvature flow has been studied in both mathematics and material science. In material science, much long before material science existed as a field, separate field. It goes back in the mathematical literature, it goes back to Birkhoff in the 19-teens, and in material science, it goes back to the 1920s at least. Here's an example, the good example to keep in mind of evolution under surface tension, so evolution under the mean curvature flow. And this is what's called Grayson's dumbbell. So you have a dumbbell, again, it's the boundary of the region. So it's in 3 dimensions, and it's this dumbbell, and you're looking at it, and so it's these 6 time shots moving in the top line from left to right, and in the bottom line also from left to right. And so you're starting with this dumbbell. Under the evolution, you see that the curvature of the cross-section here of this cylindrical region, the curvature is the mean curvature is quite large. And it's much larger than out in the bells. And so it will have the effect that the neck here will move, that points on the neck will move at a very high speed. And the neck here will in fact shrink, so it will shrink very rapidly, and then it will pinch off, and the bells have hardly changed at this point. They're moved in just a little, and then the evolution will, if you're going past the singularity, the evolution will continue, and after it pinches off, then you get these regions at the tips with very high curvature, but they will move very, very rapidly. They will smoothen out, and it will become rounder and rounder. And you see that eventually here, this is in the 6th picture, it's right before these 2 bells disappear. They will be almost perfectly round, and then they will disappear. So in this case here, you see that the evolution has 3 singularities. In this case, it's at 2 different times. The first time is when the neck is pinching off, and the second time is when the 2 bells disappear in points. So this is a good example to keep in mind. Another example that's good to keep in mind is what's called the marriage ring. The marriage ring is a thin donut of evolution. So again, it's the boundary of this donut. And and under the evolution, then the marriage ring will shrink. It will remain like a donut. It will remain a surface of evolution, and it will eventually shrink and disappear in a round circle. Okay. So now, in order to track, so how do one track if one have an evolution like this? How do one make sense of the evolution even past singular points? So past points where the mean curvature is not necessarily defined for, so a priori the mean curvature is defined at each point on the smooth surface. But what if the surface is not smooth? How do we define the mean curvature? How do we define the evolution? And so there's a technique that has been extremely useful in many different areas of not just applied mathematics, but also in all kind of areas of science and engineering, computer science, physics, medical science, all kind of areas. And that's the level set method. And the level set method is a way of tracking a moving front. And so the idea is that you think about the front that is evolving as a level set of a function. So typically you would think about the front as a zero level set. And then you want to get a PDE. And in order to get a PDE on Euclidean space, then you require that not just the zero set is evolving by this equation, but all of the level sets are evolving by the same equation. So in this case, it would be that all of the level sets of the function are evolving by the mean curvature flow. And then eventually what you want to do is you want to track just the zero level sets. So that is the level set method. And so one of the strengths about the level set method is that it allows for singularities and it allows for topological changes. So topological changes of the level sets, and also that the level sets have singularities. If the movement is monotone, so if the movement is monotone, so this means that the movement is of this surface that you want to track. If this movement move in the same direction, and then it will automatically have to move inwards because things are shrinking. So if it's moving inwards, always moving inwards, then the equation gives rise to a function that's called the arrival time function. And the arrival time function is the time when the front arrives at a given point. So if you're looking at the region that is bounded by the initial front, so the compact region that's bounded by the initial front, and if you take a point in that region, and now you're looking at when does the front, at what time does the front arrive at that point? And you defined the value at that point to the time when the front is arriving. Then you get the arrival time function. So this is a function defined on the domain bounded by the compact domain bounded by the initial front. And the level set of this function, well, that is, of course, the points where the arrival time, where the front arrived at the same time. So that is the front at a given time. And then you can ask, what equation does this function satisfy? And so this is the arrival time equation, and the arrival time equation is then a degenerate elliptic PDE. And the degenerate elliptic PDE is at the bottom of this page. Right, and you will recognize that that the divergence of the gradient of u divided by the norm of the gradient, that's the mean curvature, and then there is this, it multiplies through by the gradient of the norm of the gradient of u. And so this is a degenerate elliptic equation. It's degenerate, it's because it doesn't involve second derivative in all directions. And it is also, so that's why, and it's also, and this is really the biggest problem with this equation is that it's not even well defined when the gradient of u vanishes. And so, okay, so there's these two, it's a nonlinear equation. It is elliptic, but it's degenerate, and it's not defined when the gradient of u vanishes. So this is the complication with this equation. That is a very natural equation.
So Toby, is it only for mean convex flow?
So this here, so that's right. So this here is for mean convex flow. And so if the initial front is moving monotomally, this means that the mean curvature of the boundary of the initial front is positive everywhere. Right? So if that is not the case, then the movement wouldn't be monotone, and you wouldn't get this elliptic degenerate PDE. Okay, so now, right, let me look at the arrival time function in some examples. Suppose you're looking at spheres, at shrinking round spheres that becomes extinct at time 0. Then the arrival time function for the from the shrinking round spheres that become extinct at time 0 is this quadratic polynomial that you see here. If you're looking at a cylinder, if you're looking at the arrival time function of a cylinder, a round cylinder, that under the evolution become extinct in the line x2 equal to x3 equal to 0, also at time 0, then it's this quadratic polynomial at the bottom of the page. Okay. And so now the arrival time function, it's central in applied math. It's go back, just like the level set method, it go back to Osher and Session. It arises in various different areas. In particular, it arises in game theory. And it fits into a larger family of natural PDEs. Evans and Spook in the early 1990s, Evans and Spook, and independently Chen, Giger, and Goder, they proved that solutions exist in a weak sense, and the weak sense that they proved it existed in is in the viscosity sense. And they showed that solutions are Lipschitz. But the fundamental question is, how smooth are solutions? And examples that was known already more than 30 years ago of Tom Ilmanen show that in general, solutions are not C2. Now, let me remind you, so the weak notion that solutions was proven to exist here was the viscosity solution. So let me remind you what a viscosity solution is, or at least give you an idea of what a viscosity solution is. And there's various different notions, but they are very, very similar to what it means to be a viscosity solutions. And I'll just give you an idea here of it. So if you take a continuous function, then a continuous function is said to be subharmonic in the viscosity sense. Just let's say subharmonic at x equal to 0. if there exists a smooth barrier, so this means that there exists a smooth function v that takes the same value as u at 0. It's lying below u, and v, the Laplacian of v is non-negative at 0. So if you have a smooth barrier below your continuous function u, and it has the same value at 0, and that barrier is subharmonic at 0, then we say that u is subharmonic at 0 in the viscosity sense. And the key point about viscosity solution is that so it's a function that is just continuous, but is satisfying in some weak sense. In this case, it's a sub-solution to a PDE. And the key point is that the maximal principle extends to viscosity solutions. And an example, a sort of typical example of a viscosity solution is the function on R that is just the absolute value of x. That is, of course, continuous, and it's not smooth at 0, but it is clearly subharmonic in this viscosity sense at 0. Even the function v equal constant 0 is a barrier from below, right? That could be used in this definition. Okay, so that's a viscosity. This is one of several versions of what it means for a function, in this case, to be a subsolution. There are variants of this, but this is the simplest version. And so this is the version, sorry, this is, it's not exactly this version. Well, of course, this is also a subsolution, but more, this is this weak, it's a weak version like this, that solutions of Evans and Spook and Chen, and Godot was proven to exist for this, this degenerate equation. Now, now here's our first theorem, then that so that relates geometry to analysis. So using geometry, we can then prove optimal regularity for this degenerate equation. And so what we can prove is that the solutions to the arrival time equation is always twice differentiable, right? And recall that earlier it was proven by Chen, and Godot and Evans and Spook. It was proven that solutions was Lipschitz, but in fact they are always twice differentiable. It's already known for more than 30 years that solutions are not C2 in general, but they are always twice differentiable, and there's some bounds. They also have, we prove a bound from this for the second derivative, but the second derivative is not necessarily continuous. Moreover, we can also prove that when solutions are C2, then being C2 has a very clear geometric meaning. So if you take a solution to the arrival time equation, and that is C2, then this holds if and only if the entire front, the entire evolving front, becomes singular at the same time and then extinct. So this is exactly what we saw in the case of the marriage ring, right? So in the case of the marriage ring, you had this thin torus of revolution. Under the evolution, it stayed at torus revolution, and it became extinct in a round circle, right? So there's just one time where it becomes singular, and then it becomes extinct. Right, so this is right. So this theorem tells you that in this particular case, it's C2, and you can also see that the case of the marriage ring, does not fall in under the theorem, right? Because it's in the case of the dumbbell, it does not fall under this theorem, because in the case of the dumbbell, when you're looking at the evolution, then you have first as singularity where the neck is pinching off. So this is one singular time. And then you have a later singular time when the two bells shrink to a point, right? So there's two, in that case, there was two singular times. So it's not C2, because if it's C2, this happened if and only if it becomes extinct. The whole thing becomes singular and extinct at just one time, right? Okay, so now I want to talk a little bit. So this is like the first illustration of this interplay between analysis and geometry. So if you were just using the PDE, then the best you could do would be to prove Lipschitz, right? But if you're using the interplay between an analysis and geometry, then in fact, you can prove optimal regularity. So in this case, we're proving that the solutions are always twice differentiable, and we can even characterize geometrically when solutions are C2. By the way, it's known that there are examples where solutions are C2 but not C3. So it's a quite delicate thing. Okay. Now let me try to talk a little bit about the proof. So how do we use geometry to prove optimal regularity? And to explain that, let me just go all the way back and remind you what it means for a function to be differentiable, because it's somehow this is at the core of it. So if a function is, so one way of thinking about that a function is differentiable is that it looks like the same linear function on all sufficiently small scale. So if you take a function is differentiable at a point, it not only means that on all small scales it looks like a linear function, but that linear function has to be the same on all small scales. It cannot change from scale to scale. Okay. And so this is what it means for a function to be differentiable. A counterexample to differentiability is something like a fractal. So let me just remind you about that. So this is where you don't have differentiability. So if you're looking at, so the simplest fractal is the Koch curve, and the Koch curve is a curve that is given as a limit of an iterative procedure. So you're starting with a line, you break that line into, you're starting with this line, you break it into 3 equal parts. In the middle one, then you replace the line by an angle. And then now you have these 4 lined segments. And then on each of these 4, you do the same procedure. You take one of these 4, you take the middle third of it, and you replace the middle third with an angle. And so you repeat this process over and over again. And in the limits, then you get the Koch curve. And so the Koch curve, if this angle here is if this angle here is say close to 180 degrees, then on any scale here, the Koch curve will look like a line. It will look like a line, but as you go further down, it will look like different line, and it will look like that as you, even at the same point, as you go down in scale, what will happen is it's that line it looks like. So on each scale, it will look like a line, but as you go to smaller and smaller scale, it will look like that line have rotated around, right? So on each scale, it looks like a line, but it doesn't look like the same line on all scales, right? So this is why it's not differentiable. This is a Hilbert continuous curve, but it's not a differentiable curve. Okay, and so sorry, now, okay, so now coming back to the equation that we want to look at. So we want to look at this degenerate elliptic equation, and we want to prove, so this is the degenerate elliptic equation, and we want to prove optimal regularity for it. Right, and again, the difficulty of this equation, it's a nonlinear, it's an elliptic equation, it's nonlinear, it's degenerate, and what is really causing a lot of trouble is that it's not even defined when the gradient of u vanishes. And so yet, the main interest in this equation, or the things you really want to focus on, is the point where the gradient vanishes, so the critical point. Right? And so critical points always have to happen. If you're thinking about it as we could think about it in terms of geometry, in terms of the evolving front, but if you're thinking about it as in terms of function, right, this is the arrival time function. So at the boundary here, this function is constant. Let's say it's constant 0. And so it means, of course, that this function, there is somewhere where this function will either have a maximum in the inside or a minimum. And so at that point, the gradient of u will vanish. Right? And so the key to proving regularity of solutions is to understanding when we're at point, understanding the regularity of the solutions to this equation at point. At critical points where gradient of u vanishes. Okay, so now let me come back to what we talked about here. So the flow and u, they are smooth away from critical points, so away from point where the gradient of u vanishes. So we will focus on points where the gradient of u vanishes. And so if let's just translate so that the point that where the gradient of u vanishes is 0, that's the origin. Then if you take the arrival time function, then you can, from the arrival time function, you can generate a one-parameter family of solutions to the arrival time equation by just looking at scalings like this. So v lambda, that's a natural scaling in this equation, that u in lambda x and then times lambda to the -2. Right? So lambda here is a constant, right? But for all positive constants, this gives you another solution to the arrival time equation. And so you see that these scalings, if u here was a homogeneous quadratic polynomial, then v lambda is the same homogeneous quadratic polynomial. Right? And so in the examples, in particular in examples of the arrival time for shrinking cylinders and shrinking spheres, right, the arrival time function was a homogeneous quadratic polynomial. And so these are then invariants under this scaling, right? They are independent on lambda. And now we want to prove that the solution to the arrival time function, that any solution, is twice differentiable. So twice differentiable, and so we may as well prove, we want to prove this at any, if you are away from critical points, then it's classical that solutions are twice differentiable. So the whole problem is at critical points. And now, in order to prove that it's twice differentiable, you want to prove that there is a second order Taylor expansion. So what we want to prove is that if you're looking at these rescalings of the solution and you are blowing up, so that means that you are looking at rescalings where lambda here goes to 0, then we want to prove that this here has a limit, that the v lambda has a limit as lambda goes to 0. And a priori, there's no reason to expect a limit even for a subsequence. Okay. Briskin, Ilmanen, and Wright, they proved that you get geometric blowups, but those depends on the choice of subsequence. And so what they showed is that that when you're blowing up, then you get a geometric limit, and that limit is dilation invariant, and that means that is what's called a shrinker. Most shrinkers are non-compact. Okay, now of course so the problem is then, so we're getting that we're getting this geometric blow up. So this is like saying that the level sets, if you're looking at level sets, then the level sets converge in some weak sense as sets, that they converge to something, but it converge depending on the choice of subsequence. So if you choose a different subsequence, it may converge to something different. Okay. And so the question is, could it be like the cock, where the sequence of rescalings, if you take one sequence of rescalings, then you get one blow up. Whereas if you get another sequence of rescalings, then you get a different blow up. Okay. For monotone flows, it has proved by the combined work of various people that the possible geometric limits have been classified. So they are spheres or cylinders. And so this is work of this group of people. And this classification rely on a matrix maximal principle of Hamilton. But the question that remains is, do limits depend on the choice of subsequence? So are limits unique, or do they depend on the choice of subsequence? Could different subsequence that you're blowing up will give a different limit. And so this is illustrated in this picture, where the yellow cylinder is that you have one sequence of blow up, and then you get this yellow, and then you take another sequence of blow up, you get maybe the blue cylinder, and a third sequence of blow ups, and you get the red cylinder. Right? And so this is again just like in a cock, where for each limit, each blow up, then there's a subsequence of blow up that converge, but the limit depends on the sequence that you choose. Okay, and so the thing is that in this case, you don't have that, and so Bill and I proved that you get uniqueness of blowups for monotone flows. So the level sets will converge will converge. It's not like the convergence doesn't depend on the choice of subsequence.
Toby,
yep.
This earlier result was not like so you told us Brian Weiss and other people's result for it depends on the sequence.
Yeah,
it's for the earlier. Is it not for monotone flows, right? It's just general flows.
No, this is for monotone flow. This is for
the Brian Weiss and
that's for monotone flow. Yeah.
But in that geometric blow-ups, it depends on the sequence.
It depends on the sequence. It's established by very weak techniques. It uses monotonicity. It uses what's called Briskin's monotonicity. And it's like a classical thing that if you're using monotonicity like that, all you can hope for is that for each sequence, there's a subsequence that converge. But you can never, but that's never enough to give uniqueness.
I see. Okay.
And again, this result of Wiskin, Sinstrai, Brian White, and these other guys, they are for monotone flows.
Okay, thanks.
Right. Okay. So now, right. So so Bill and I proved that that you actually get uniqueness of blowups, so that the blowup does not depend on the choice of subsequence for monotone flows. And so this kind of questions about uniqueness, this have long been recognized in geometry as fundamental. There were key early work by Allard and Almgren and Leon Simon on uniqueness questions for minimal variety. Okay, but one of the key problem here in this case is, so in all of the earlier work, the blow up is always compact, and in this case, blow ups are typically not compact. So none of the techniques developed can be used in this case. Right, and so from uniqueness, we can then prove that that at a singularity, so and analytically, a singularity is where the gradient of u vanishes. Then u looks like the same quadratic polynomial on all small scales. So this gives a second order tail expansion and twice differentiability. Okay. Now let me talk a little bit about some related questions. So common in nonlinear PDE is that solutions are not smooth. They have singularity. And so in the case of the equation we looked at, for instance, the case of the evolution of the marriage ring, then we have that the singular set is a curve, right? That's where the marriage ring becomes singular. It becomes singular in a circle, in the central circle, and then after that it becomes extinct. So there's this circle for the marriage ring under the evolution. There's a circle of singularities, and in fact, it was proven by Brian White using dimension reduction that in R3, if you're looking at the evolution of a surface, a monotone evolution, then the singular set is always one-dimensional, but it's one-dimensional just in a measure sense. It doesn't necessarily say that the measure is finite. So the measure could be infinite. And so this is just like that the Koch curve is kind of one-dimensional, but it has infinite length. And so now using the uniqueness, we can prove that in fact that the singular set has a finite one-dimensional measure. So it looks like that. It looks like the union of C1 curves together with something of lower dimension. Okay, so it has C1 curves with finite length together with something of lower dimension. And similar results, get similar results in all dimensions. I just for simplicity stated this in R3. So this is another use of uniqueness, right? That gives you this strong structure of the singular set, the set where the solution is not smooth. Now another, so I only have a few minutes, 3 minutes left, maybe not even actually. Should I stop or should I?
No, go ahead. Yeah.
Okay, so let me just say, so I wanted to talk initially about three different, and I certainly won't get to all of them, but I'll just say a few words about the second. So I wanted to talk about the interplay between analysis and geometry in three different areas. The first area we discussed was proving optimal regularity of solutions to non-linear PDE using the geometry. The second topic here is dynamics and stability of solutions. So, uniqueness can be understood dynamically for rescale flows. So a rescale flow, this is where you looking at the flow, but as you're flowing, you continuously magnify. So if you continuously magnify, then you can think about uniqueness as a solution to the rescale flow, that the solution to the rescale flow has a limit point, that if it has a limit point, then it has a unique limit. Okay, so this you can reformulate uniqueness in terms of the rescale flow, that if it has a limit, then it has a unique limit. And so this contrasts what's called wandering point in dynamics, points that may have limit points, but then but they go back to the same limit point, but they go away from it, and then they go all over the place, and then they come back to that point again. Those are wandering points in dynamics. Okay. Now the rescale flow you can think about as a gradient flow. So it's a gradient flow for what's called the Gaussian surface area. So this is where you're taking a submanifold and you are integrating a Gaussian over the submanifold. And so the monotonicity that I alluded to earlier, that was used to prove that you got geometric blow-up. This can be used to prove that this functional f is monotone under the rescale flow. And then you can think about singularities at the origin. You can think about those as critical points for this functional f. And you can also think about them, if you will, as equilibrium point for the rescale flow. There's another very natural functional that we call the entropy, and that's when you take the soup over all Gaussians with different centers and different scales. And so using this monotonicity, you can show that the entropy is a Lyapunov functional for not just for the mean curves of flow, but for all rescaled mean curves of flow. Okay, let me just finish with just talking about, this with unstable structure, and then I'll finish. So again, one of the key in many areas of PDE and dynamics, you were interested, you have so many solutions to the equations, and you want to somehow narrow down the ones that are physically relevant. So what are the physically relevant? The physically relevant, those are the stable solutions, right? The unstable ones, those you wouldn't see in nature. And so you could ask, so we know that when we're running this mean curves of flow, we're getting singularity. And so now we are just in the general case, we're not anymore looking at monotone flow, we're just looking at any flow. And you can ask, what are the singularities that are stable? Which one will physically happen? And the other ones the other ones are the singularities that can just be perturbed away. And so what Bill and I proved there is that in general, so this is for all flow, not just for monotone flow, that in general, the only physical relevant, the only generic singularities are shrinking spheres and shrinking cylinders. in all dimension. Okay. And so I'm already over time, so I'll just skip the rest of the sample I planned. Thanks very much for your attention.
Yeah. Thank you very much for great talk, Toby. Let me applause for everyone. Okay. Questions? Okay, let me break the ice. For the, generic singularities here, what do you mean by perturb away? When you change the initial condition just a little bit, you can get away from this other singularities?
That's right. So
Nice.
it's fine. And the key point here is that right, that you want to right, you could change if you take a singularity, you could change it ever so little. But what you don't want to happen is that you don't want to see the same singularity, not at that particular time when you saw it before, but at a different time or different point in space, right? That wouldn't qualify. Then it's the same singularity. So when you're talking about generic singularity, you're talking about singularities that where you're making some perturbation, then you don't see that singularity at all, right? It's very, for any singularity, you could just make some small change, and then you may see the same singularity at a different time or different point in space. Now that's not a really very interesting perturbation, right? So when you're talking about generic singularity, you're talking about singularity, you're making some tiny perturbation, and then you would never see that singularity, not at that time, not at any other time, right? That's a generic singularity. Right?
Okay, since you mentioned, if I give you an initial surface or something like that, can you tell me what kind of singularity I must see later?
Right. So I mean, for a given one, right? For a given one, there's no way of telling it, right? Because there's infinite many possibilities for singularity. If the initial surface was mean convex, then you can tell. But in general, you couldn't, right? And there are infinite many singularities that could happen in general. And so that's why, in general, if you're not looking at a monotone flow, you are interested in what are the physical relevant singularities, right? And the physical relevant ones, those are the generic ones, and those are only spheres and cylinders. And when I'm talking about cylinders, I'm talking about a round sphere cross a Euclidean factor. So it's like what we call a generalized round cylinder. So it's in any dimension. So in our tree, it would just be a two sphere or a cylinder. But in higher dimension, it could be a sphere of some dimension cross a Euclidean factor of the complementary dimension.
Okay, thank you. Other questions from the audience? Okay, so let's thank the speaker again. Thank you very much, Toby. It was a great talk.
Thank you.
Thank you for very much. Yeah. Maybe we can stop recording. And